Hey, what's up all you guys out there in math homework land? Hope you're doing well. I hope it's not midnight or past midnight, and I hope you had a good dinner and a nice break from school. We're talking about rational exponents today, and we talked about these in class. There's a couple pretty important ideas here. We'll see if we can kind of break them down for you into small chunks. In class, we talked a lot about why and where this stuff comes from, and did a little bit of explaining on the background. But one of the things that we need to know is what's called the rational exponent property. So this is our 8th property of exponents. I'm going to write it right here so we can use it. The rational exponent property is what allows us to convert between radicals or roots and exponents. And sometimes it just happens that it's easier to use exponents. We are familiar with how exponents work. We have 7 different properties of exponents. This is like our 8th now. And so we know about like product property and quotient property. And so sometimes when we see things that have roots in them, it's a little bit more convenient to just change it to exponents. And this is how that works. So if you have a root, that root will have an index number. And so we're just going to call it n here. Sometimes that's a square root, like a 2. Sometimes it's a 3 or a 4 or a 5, but every root's going to have an index number. And if you don't see it, then you know it's automatically a 2. All right, then you have some radicand, something inside the radical. And you could even have an extra exponent outside. And when you have something like this, you can convert that to an exponent. It just happens to be that the exponent is going to be a fraction. So the numerator of that fraction is the power of that root is being taken to, and the denominator of that fraction is the index number of the root. Now there's actually 2 ways to write something like this. It's equivalent to do, this has to do with another property of radicals that we talked about yesterday, but you can have that power on the inside. Those are equivalent expressions there. So if you have something like this with the power on the inside, again, the same idea. Okay. Now the way I try to remember this is that the root of a tree is on the bottom. So whenever I see the root number, or we'll call it the index number, but it's the number that's in the root here, that's going to be the bottom number, just like roots are on the bottom of trees. So power goes on top, roots go on the bottom, just like trees. And one of the ideas here is just rewriting these, just changing them to back and forth from exponential form to radical form. So you'll see exponential form. That means we want to write these with an exponent instead of a root. We know that exponent is going to be a rational exponent, or in other words, a fraction. And here we're going to write them in radical form. So I'm just going to make a little note to myself that these are going to be rational exponents, or fractions. And down here we're going to have roots. Okay, that's kind of what we're doing. So back and forth. All right, now 1 is actually maybe like, of the problems here, it's actually maybe the trickier of the 2. It looks kind of basic, but there's a couple hidden numbers here. So you have a root 2, right? The default root, if you don't see a number there, we just assume it's going to be a 2. And we also don't have like an extra power, either on the inside or the outside. But, you know, if we want to, we can always just put a 1 right there, k to the 1. So based on this little formula here, this property, the power becomes the numerator, and the root number, the index number, becomes the denominator. So I can rewrite this square root of k as k to the 1 over 2. So we have an exponent, it's just a fraction. Okay. Now here on number 2, we actually see the index number, it's 6. But again, we don't have an exponent that we can see. So we can either put a 1 here on the x, or we could even put a 1 on the outside. It doesn't really matter where that exponent is in this context. So either way, we're just going to have an x to the 1 over 6 power. That's how we rewrite that. Okay, this one's a little bit easier. We can see all the numbers that we need to use. So the power is 2, the root number is 3. Remember, roots go on the bottom, so roots on the bottom, power's on the top. Another thing to consider is that the radical, the symbol here, is a grouping symbol within it itself. So when I'm taking the 3rd root of this stuff, it's almost like this is in a set of parentheses. So when I rewrite this guy, I'm going to have 10n as a product, and that's going to be raised to the 2/3 power. So the power number is the top of the fraction, the root number is the bottom of the fraction. And I could go further if I wanted to, and I could apply this 2/3 to both the 10 and the n, but we're not simplifying here. I know it kind of seems like we are. What we're doing is we're just learning how to go back and forth between these two different worlds, between exponents and roots. A lot of problems it's easier to be here than it is to be here, but we need to be able to go back and forth and convert. So these aren't necessarily simplified. We're not simplifying here, we're just converting it to a different form. Alright, so here we got 2x to the 7/4. Again, the 2 and the x, we have both of those we're taking the root 4th root of both of those and then taking that to the 7th power. So we need to keep 2x as a product, taking that to the 7/4 power. And this is going to be 5b to the 4/3 power. Okay, that's it. Not too bad. All right. In the next 6 problems, we're just going to do the exact opposite. So top number becomes the power, the bottom number is the root or the index. So I have the second root of x to the 1, or the second root of x with the 1 out here. But either way, we don't really need to write the 1, and we don't really need to write the 2. Those are both numbers that we usually don't write. We just assume that that's a square root or a 2 root, and we know that that's x to the 1. So this is actually what we're going to write here. Okay, over here we're going to have the 4th root of b to the 5th, but there's actually 2 ways to write this. We can do the 4th root of b and put the 5 out here. Those are equivalent. Sorry. Let me show you what I did there. Okay, those are equivalent. So keep in mind there's a couple ways to write these sometimes. Alright, so we got the the square root of k to the 3rd power. Also equivalent is the square root of k with the 3rd power on the outside. But typically when we, write a root, if we don't absolutely need to write a number, we won't. So square root of k to the 3 we can write like that, or we can also write it like this. We just don't write that index number. I'm just showing you where that 2 would go normally, but again, we don't always write that index number 2. That's kind of the default. Okay, here we have the 5th root of n to the 7th, or the 5th root of n to the 7th. Okay, now we got some grouping symbols. So in this case, we're going to have the 3rd root, and then we're going to have 3x inside. Now we could put this to a power of 1, but we don't really need to write that power of 1. And if we don't have that power of 1 there, we don't need to write the parentheses because the radical symbol itself acts as a grouping symbol. We just have to make sure the 3 and the x are both under that square root bar. Alright, now this guy here, we're going to have a root. It's the 5th root, right? The 5th root's on the bottom. And then we have 2n. Now this time, we have the parentheses and we have the 2 here. So this is actually going to change things a little bit, because over here was a 1, it doesn't really matter. But here with this 2, we can actually, simplify, or we can go further if you wanted to. Now if you stopped here, that's probably okay, because again, the point is to not simplify. The point is to just practice converting. But if I wanted to apply this 2 to both of these factors here, I would have the 5th root of 2 squared and n squared. And then I would probably turn that 2 squared into a 4, because 2 times 2 is 4. So I think I wrote it like this on the answer key, but if you have something like that, that's probably okay too. So it doesn't say simplify, it just says we're just converting, we're just practicing. Now on the next few, excuse me, we actually are going to simplify. Okay. Notice here that we have some opportunities to apply properties of exponents, and specifically the ones that I wanted to practice were the product property and the quotient property. Excuse me, product property and power property. So we're going to treat these rational exponents just like we would any other exponent. We actually already know what to do in this situation. The only difference is that we have rational exponents. And I just want to show you that it's not, it looks scary, but it's not even that bad. So remember that there's a 2 multiplying this v, right? Those aren't necessarily inseparably connected. We can break those up. So I have a 2 up front, and then I have all these v's. And we know what happens when we multiply things with the same base, we add the exponents. So what we need to do is we actually need to add all of these fractions together. So we're going to have 2 times v, and the power of v is going to be whatever the sum of these exponents are. So I can do that really in any order. These are the 3 that I have. Okay, since these have common denominators already, I think I'll go ahead and do those first. So I have 3/4 plus, this is going to be 4 halves, so 3 plus 1 is 4, over that common denominator of 2. But now I need common denominators to add these guys, so I'm going to use my multiplicative identity property, because that's really just 1. Multiplying by 2 over 2 is really just 1. So we got 3/4 plus 8/4, and that's going to give me 11/4. So the power on this v is 11 over 4. And the instructions tell me to leave it in exponential form. So although we could turn that back into a root and kind of make sense of that, what that rational exponent means in terms of square roots and things like that. This will actually be a 4th root. We're going to leave it like that. Okay. All right. Similar idea here. I'm going to start by using the commutative property to move some stuff around. So the 4 times the 3, we'll just put the 4 and the 3 up front. That's going to be 12, so that's no problem. Okay, then we have n, and we just need to figure out what this sum is. So we're going to add 2/3 and 1/4. Again, we need common denominators. So I'm going to use my identity property here to get common denominators. So 8/12 and 3/12 is going to be, another 11. 11/12 in this case. All right, not too bad. Now in these situations, I'm going to want to multiply. This is the power property that we're doing. So I would multiply 2 times 7/4. So just as a reminder, if you want to multiply a fraction by a number, you usually just turn that number into a fraction by putting a 1 on the bottom, and then you multiply straight across. Now we also talked about cross-canceling, because remember, this is going to give us a 14 over 4, but if there's any factors that go into these like diagonally, we can cancel those as well, because all the factors of 7 and 2 are going to end up in the numerator, and all the factors of 4 and 1 are going to end up in the denominator, and eventually we're going to have a 2 over a 4. So back from here, from the beginning here, I could say 2 goes into 2 once and 2 goes into 4 twice, and I could simplify there, right? I would also be the same thing as doing that here, and so I get 7 times 1 over 2 times 1, or 7 times 1 over 2 times 1. So either way, you're going to get 7 over 2, and that is our exponent. All right, in this case, we're going to have to multiply the exponents. This time we already have, 2 fractions, so multiplying straight across, we get, nothing cancels. So we get 2 on the top, 2 times 1. On the bottom, we get 3 times 3, which is 9. So r to the 2/9. Okay, so it's exactly the same thing we've been doing before. I don't know, 2 weeks ago when we talked about the product property and the power property, we knew what to do. Multiply the exponents, right? Add the exponents. We knew the situations in which to do those different operations. We're just kind of applying that to rational exponents now. All right, so here we're going to have a couple different things to do. So we're going to have to do 3/2 times 2. Okay, again, we can cross cancel here. So we got the 2 canceling with the 2. That's the multiplicative inverse property. And that leaves us with 3 times 1 over 1 times 1, or 3 over 1. So this first fraction here, when we do a 3/2 times a 2, that comes out to be a 3, or 3 over 1. Okay, so multiply the exponents first. Now we have to add the exponents, because this is now the product property scenario. So I got 3 over 1, and now I'm adding 7 over 4. So multiplication and addition work differently with fractions. Multiplication, you don't have to have common denominators. Addition and subtraction, you have to have common denominators. So using my identity property here, 12 over 4 plus 7 over 4 is going to be equal to 19 over 4. So just putting 12 plus 7, which is 19, over that common denominator 4. Okay, now again, we could turn this back into a root. We could actually write this number as a mixed number if we wanted to, but we're just practicing with the properties here. All right, let's take a look. So we're going to have to multiply these numbers. So I'm just going to go off to the side again. 3/4 times 4 over 1. Okay, I'm going to cross cancel here. That gives me a 3 into the 3. And then we have this guy. So 2 times 1/3, or 2 over 1 times 1 over 3. 2 times 1 is 2, 1 times 3 is 3. So I multiplied these exponents together, I multiplied these exponents together, now I'm here. Okay, but now since I have n's and n's, I gotta add the exponents. So I have 3 over 1 plus 2 over 3. And don't try to cross cancel here because this is a plus, not a multiply. That cross cancel only works when we're multiplying. But we do need common denominators. So this is going to be 9/3 plus 2/3, which is 11/3. Lots of 11s coming up today. So since 3 plus 2/3 was 11/3, that's my final power of n. Okay. Now this next one, we've actually already done problems like this before, but I want you guys to practice using rational exponents here. And it's not to make you do double the work or you know, to confuse you or whatever, but what's coming at you when you get to like SM3 and advanced algebra topics is you need to have a robust toolbox. You need to have lots of tools to be able to apply to different situations. So there's some situations where radicals are just not going to be your go-to method. They're just not going to come out very nice, and it's much, much easier to use rational exponents. So I want you to try to deepen your understanding of what's happening here with the roots, the radicals, and I also want to give you lots of tools and ideas that you're going to see again in SM3 and Math 1050. So we're going to just kind of repeat this idea, but we're going to look at it from a different perspective. We're going to look at it from a rational exponents perspective. Okay, so we won't do all of these. We did all the other ones that were pretty short, but we'll take a look at a couple of these, and I think maybe we'll do the evens. Well, actually, I gave you all the. Did I give you all the answers? I gave you the odds, so yeah, I'll do the evens for you here. All right, so the first thing I would do here is the same as I would do in another situation. I would prime factor the number part. So we got 54. We know that's 6 times 9. There's other factors in that, of course, but those are the ones that come to mind. And I got 3 and 2. Those are both prime, so I stop. I can't divide those out anymore. And then we have 3 and 3. Okay, so I have 1, 2, 3 3s and a 2. Okay, so let's rewrite this guy. I'm going to rewrite it as square root. I'm going to put a 2 out here. And I got 3 to the 3rd. And I got 2 to the 1. And I got u to the 3rd. And I got v squared. So everything's to a power. And now what I'm going to do is I'm going to use those rational exponents. Okay? So I'm going to convert everything to a fraction. Now this guy, the index, the invisible 2, that is actually the index number here, is the denominator for all of these guys. And the numerator is the power here. Okay? So I have 3 to the 3 over 2. And I have 2 to the 1 over 2. And I have u to the 3 over 2. And I have v to the 2 over 2. Okay? Now that it's in fraction form, you can see that some of these fractions are going to simplify. Like 2 over 2, for example, that's just 1. We also can notice that some of these improper fractions, the numerator's bigger, they're going to turn into mixed numbers. Now usually we don't use a lot of mixed numbers in algebra, but in this case it's actually kind of helpful. 3/2 is actually 1 1/2. And so if possible, we want to give these numbers or these variables, we want to give them whole number or integer powers. So when I see this 3 to the 3/2, I'm like, oh, okay, so there's a 3 to the 1 and there's a 3 to the 1/2. All right, this is an integer exponent, which is kind of nice, and this one is a rational exponent, which we'll have to turn back into a root. So this 3 to the 2/3 actually, 3 to the 3/2 became two different base 3s because this is the whole number part and this is the leftover part. All right, so 2 is going to work the same way. I can't really break it up, but there's just the 1/2 part. U, again, that's 1.5. 3/2 is 1.5. So I have a u to the 1, and I also have a u to the 1/2. I'm just kind of splitting up the whole number exponent from the rational exponent, from the pieces. And then, of course, we had v to the 1 because 2 over 2 is 1. So we have some of these guys have whole number exponents, which is great. That just means they're just, you know, regular factors. So I have a regular old 3. I have a u to the 1. I have a v to the 1. Okay, now everything that's left over that has a rational exponent is now going to go back inside the root. So the last part says convert your final answer back to radical form. So we're using rational exponents to help us understand, you know, how things are canceling and whatnot. But when we put it back into the root, the bottom number, 2, 2, 2, that's the index number. So I'm not going to write the 2 there because we don't usually do that, but this is a square root, so that the fact that there's a fraction with a 2 on the bottom tells me that this needs to be in a root, the rest of the stuff. And then I have 3 to the 1, or just 3. I have 2 to the 1, or just 2. And then I have u to the 1, or just u. So you might be wondering, well, where did the 2's go? So I have 3 to the 1, 2 to the 1, u to the 1. Well, the 2 is this number, right? It's the root number. The denominator of those fractions is the root number. So altogether, I have 3 times u times v. Careful with those u's and v's because they look kind of similar. And then I have the square root of 6u. We can do 3 times 2, so we're just going to finish that up. Okay. So it's kind of interesting to think about it from this perspective because, you know, going back to the up here, we talked about it in class today. If you look at this number, the index number 2, and it's smaller than the power, or at least the same size, you know for sure that that base is coming out. So like 2 is smaller than 3, so I'm definitely going to have a 3 on the outside. And 2 is smaller than 3, so I'm definitely going to have a u on the outside. And 2 is the same size as 2, so I'm definitely going to have a v coming out. Remember that the square root, or the 2 root, is the inverse of the 2 power. And so those kind of undo each other. So just another way to think about it. And when somebody asked me today, like, well, how do you do it normally? And I kind of do like a hybrid. This is what I'm kind of thinking in my mind as I go through the process, but I'll just be like, okay, 2 goes into 3 one time, so I have a u on the outside, but there's a remainder of 1, and so I have a u on the inside. So I'll kind of talk about that a little bit more as we go. Let's look at 22 as an example. So just without doing anything right now, just looking at it, does 4 go into 6? Yeah, it does. 4 is smaller than 6. And so I'm definitely going to have x's on the outside. Now, let's kind of predict. 4 goes into 6 one time with a remainder of 2. So what I'm thinking is I'm going to have an x to the 1 on the outside, and I'm going to have a remainder of 2, so I'm going to have an x to the 2 on the inside. That's my prediction. Okay, I can do something similar with the y's. 4 goes into y one time with a remainder of 3. So I'm going to have a y to the 1, because 4 goes into y one time. Sorry, 4 goes into 7 one time. And then there's a remainder of 3. I'm going to have 3 left over on the inside. So, and this is a 4th root. So that's kind of what we're gonna have there. But I want you to show the rational exponents just because it's going to be good practice to understand how to use those. We're actually going to use those later this week as well. So we kind of jumped the gun here, but let's go ahead and let's factor the 243, and then we'll kind of do the rest of the rational exponents. Okay, so 243. I'm not sure all the numbers that go into there, but I'm pretty sure that 3 will go into there. So I'm going to just divide. Now this part, if you want to use a calculator for, that's fine. I just don't want you to shortchange yourself by using it for everything. So I'm still going to prime factor here. Turns out that this is 3 times 81. That's prime. And then we have 9 times 9. which is a 3, a 3, a 3, and a 3. So it looks like 243 is actually 3 to the 5th power. So I have 3 to the 5th, and I have x to the 6th, and I have y to the 7th, and I have fourth power. So let's turn these into rational numbers, okay? Just to see what's happening here. So 3 to the 5/4, x to the 6/4, y to the 7/4. Okay. Now we'll turn these into mixed numbers. Now we could simplify 6 over 4 if we wanted to. We could simplify that to 3 over 2. Let's actually, so this is actually an interesting situation. Even though this will simplify to 3 over 2, we actually don't want to simplify it here. And the reason why is because at the end of the problem, we want to be able to put everything back into the root 4 again. And if the denominators don't match, then we won't be able to put them all back into the root 4. So even though it's really tempting to want to simplify that, and I would want to do the same thing, we want to leave them actually with denominators of 4. So let's go ahead and fix those. 5/4 is 1 and 1/4. So I have a 3 to the 1, and I have a 3 to the 1/4. Okay, 6/4 is 1 and 2/4. So I have an x to the 1, and I have an x to the 2/4 as like the remainder. Again, we're going to leave those as fourths. You'll see why in a second. All right, the next one here we have 7/4, which is 1 and 3/4. So I have y to the 1, and then I still have a y to the 3/4 left over. Okay, so this guy, 3 to the 1, x to the 1, y to the 1, those are all just regular factors. Those will be on the outside. Okay, now what's left, we have these rational exponents, and the denominator is 4. So the reason why we didn't simplify 2/4 to be 1/2 or 6/4 to be 3/2 is actually because we want the denominators of all these to match so that we can say, oh, they're all root 4. So from here, since we have all the 4s on the bottom, that's the root number, we have a 3 to the 1, we have an x to the 2, and we have a y to the 3. Okay, so not too bad. I know some of you guys are already kind of see the pattern that's happening, but like I said, we're going to use rational exponents tomorrow, and I want to make sure that we understand how those work, because I think thinking about rational exponents will help with what we're going to do tomorrow. Okay, let's do a couple more problems. We'll do the rest of the evens here. So let's prime factor 32. Okay, that is 16 and 2, which is 8 and 2, which is 4 and 2, which is 2 and 2. So 16 is actually, sorry, 32 is actually 2 to the 1, 2, 3, 4, 5. 2 to the 5th. So we have the third root of 2 to the 5th, u to the 4th, v to the 4th. Okay, sorry, that looks like a 25. That's a 2 to the 5th power. Okay, converting to rational exponents. 2 to the 5/3, u to the 4/3, v to the 4/3. Okay, let's change them into mixed numbers. So 5/3 is 1 and 2/3. So I have 2 to the 1, and I have the leftovers, which is 2/3. So there's a whole number here. Because 3 goes into 5 one time, but there's 2 left over. So we have that fraction as well. Okay, 4/3 is 1 and 1/3 as a mixed number. So I have, I have u to the 1, and then I have u to the 1/3. Same with v. 4/3 is 1 and 1/3. So I have v to the 1, and I have v to the 1/3 power. So just separating out the whole number parts from the extra. Like, again, just to explain it a different way, 3 goes into 4 one time, but there's an extra 1/3 left over. So I got a 2, I got a u, I got a v on the outside. Those are just regular factors. What's left over with fractions are these things, and they all have denominator 3, which means that my final root here is going to be a third root. And what's left is a 2 to the 2, a u to the 1, and a v to the 1. And since 2 squared is 4, I'm just going to write that. So 2uv times the third root of 4uv. Just like that. All right. Let's do one more, and we'll call it a video. All right, 2D, it looks pretty big. I don't know what goes into it. Definitely 2 because it's even. Let's start there. Oh, that's going to be 144. okay, which is 12 and 12, which is 3 and 4. Circle my primes here, and then each 4 is a 2 and a 2. So we have 1, 2, 3, 4, 5 2s, and then 2 3s. And this is a square root. So we got the square root of, let's see, count again, 1, 2, 3, 4, 5. 2 to the 5th, 3 to the 2, x to the 2, y to the 3. Remember, this is the square root. I'm going to put a 2 there. That's our denominator. So going back to rational exponent form, we got 2 to the 5 halves, we got 3 to the 2 halves, we got x to the 2 halves, we got y to the 3 halves. Okay, let's change those improper fractions to mixed numbers. 5 halves is 2 1/2. So I got a 2 power and I got a half power. So I'm splitting that up into 2 to the 2 and 2 to the 1/2. That's 2 1/2. I have a 3 to the 1 power here, those cancel. I have an x to the 1 power here, those cancel. And then y, this is 1 1/2. So I have y to the 1, and then I have y to the half. All right, so regular number, regular factor. So 2 squared and 3. So I'll put those up front. I got a 2 squared, I got a 3 to the 1, I got a y to the 1. And then, oh, I got an x in there. Okay, and then what's left over is whatever has a rational exponent still. So those are going to get converted back into roots. Since the denominator is 2, it's going to be a root 2. And then I have a 2 to the 1, or 2, and I have a y to the 1. So let's put this all together. 2 squared is 4, times 3 is 12. 12xy times the square root of 2y. Final answer probably doesn't need that 2 index. That's just kind of for us to work with. So that's 4 of those. All right, so again, practice with your rational exponents because that is going to be a strategy that's going to come in handy. I know that there's other strategies to do that, but I want you guys to be flexible with your thinking so that you can use this tool in different situations. All right, thanks for watching, guys.